just get this streaming and make sure it's coming through. And we're now on. No, I'm not actually showing anybody else here, so I'll trim this bit at the front. So, okay, we're live, and this is welcome to our first streaming presentation of Oxford Information Lab's Lightning Talks about topics that matter to people at Oxford Information Labs, new staff, our colleagues, our friends and customers, and the general public. We just want to share these little nuggets and things. My name is Lucian Taylor. I'm one of the product development team here at Oxford Information Labs and one of the founders. And it's very good for us when we're working with new people to sort of recap on the things that matter to us. Today we are talking about the internet network and the domain name system, what we call the DNS. These are a huge subject in their own right, and we could go on and on for hours, but we've just picked out, or I rather have picked out, 20 minutes worth of stuff that I feel matters to us and our team at this moment in time. Obviously these will be updated from time to time. So here we go, Internet, Network and the DNS. So on the internet is a vast network of networks connected to by all sorts of machines and people. On the internet, nobody knows you're a dog. It's a place where you can just occupy some space and broadcast whatever you want to broadcast. What makes the internet different? Why is the internet different? Well, it has no centralized control. It has what we call the end-to-end principle as a network. It has an ability to have permissionless innovation, so you don't have to ask anybody to do anything to sort of connect it to the internet. You don't have to apply for anything. It is big, it is international by nature, and it is what we call a trusting network. So let's look at these sort of pick out these sort of things. Centralized control. The internet was invented, and we're not really going into the history of the internet at all, really, today. But it was invented to survive potential nuclear attack, and it is very like it has no sort of center point that you can kind of attack and disconnect everything. It is a grid system. It is a network of interconnected networks, and we have what's called the end-to-end principle, where data wants to travel from one part A to part B. It can go through a myriad of journeys that are determined and self-determined on the way. So there's no prescribed way of getting through the internet, so that any part of the internet can be kind of taken out of play, and yet you still have a survivable internet as a grid system for data to use. Permissionless innovation, well, we've seen the internet now being used by big monetizing organizations like Uber. Nuclear power stations are connected to the internet, or little kind of free development programs. Raspberry Pi software open source developers are able to connect to the internet and use it, and they're all on a kind of equal footing, and nobody has to ask anyone else for permission to use this wonderful network. It is international by nature. It's not part of some geopolitics region or particular country. It's there for everybody, for the whole world. Obviously some areas still have very poor connectivity, but it is meant to be for everybody. This is you'll notice some graphics are injected into there by our wonderful Patrick Taylor. This one, I said I want a trusting network. What can I have as a graphic for a trusting network? And he sort of thought of a border control guard server having his coffee with the gate open, and everybody's allowed to walk through. You know, we don't verify who people are or how much we can trust them. It's a bit like roads. Criminals use roads, and lawful people use roads, and you don't check them out first. So as we move on away from the sort of the things that are different about the internet, we think about we need a model for analysis. A useful model for analysis is for us to think about the internet as 4 layers. I'll explain. I'll start from layer number 4, which is the one that we like and we're most familiar with at Oxford Information Labs. We do a lot of work at what we call the application layer. The layers are particularly interesting from looking through this lens because we're looking at them from the point of view of protocols that govern how the internet works. If you think of the internet, it's not really a rigid set of devices all connected that sort of are built in the same way. They are all built and interact with each other, and the software interacts with each other because it all follows whole clusters of protocols that have been developed at the different layers. Layer 4 is the application layer, and they're what we call app protocols. Level 3 we have what's called the transmission control layer, the transport layer, and I'll explain these in a bit more detail. Layer 3 is the network layer, and layer 1 is the physical layer. So we start with the lowest layer, the physical layer, and what matters here are what we call link and address resolution protocols, and this is really sort of far away from what we do at Oxford Information Labs, but we call this the bottom of the stack. And so the protocols that matter here is not like a Cat5 cable or a particular sort of laptop. It's what matters in terms of internet technology at this level, and people that are developing Cat5 cables or ports or Ethernet ports need to be aware of the Ethernet protocols, the internet protocols that govern these sort of devices. The other protocols that matter at this level are address resolution protocols, which map what we call IP addresses, which are internet addresses, to unique addresses for any particular device that's connected to the internet. Luckily, we're not down at this level, and I really this isn't really the kind of work that we particularly aspire to, but it's important to know what our software depends upon and what it's built upon. And also in those of us doing research, it's important to know that these protocols, these standards, are very, very critical in our world. Layers 2 and 3 are often referred to together as a bundle. They're called the TCP/IP Internet Protocol Suite, and this is really the heart of the internet, the heart of innovation here. So layer 2 is the internet layer, which is what we call the internet protocols. So this is what we call the internet protocol part of TCP/IP, and these are effectively the rules governing the format of data, how data is structured as it goes through the internet. Let's think a little bit about that. So it's the rules governing the data between that travels between a source, if you think of that end-to-end principle and the grid network, and its destination. The data can be thought of as a bit like fragments of data equivalent to Paddington Bear. He's kind of wandering through a network and he doesn't really know where he's going, and he doesn't really know the route he's on. There is an important difference between Paddington Bear when we think about data in terms of its structure. It's not Paddington, because Paddington just has a label. It doesn't really have a destination address. He doesn't really know where he's going, and he doesn't really know where he's come from. Also, the payload is very different with Paddington. With Paddington, you see Paddington as a whole entity here. If we can talk about this, with the internet, we're breaking up objects into small components, and then we're reassembling them again, so that when it goes through the transport, it's going in a very regular and repeatable way. However, the packets of data are not broken up in the way that Mrs. Potato Head is. The packets of data are broken up into a very regular and uniform way. They're not particularly like a jigsaw puzzle, but they do sort of fit together at the end and reassemble a what we call a software entity. They're more like units on a container ship, where they contain they are packed in a very, very regular way, and so you don't really have to give any special treatment to what's in them. You just move them as a regular unit, and that means that a myriad of unknown actors, what we call nodes on the internet, can deal with data packets and know what to do with them because they're a regular size and shape. So a better metaphor for Mrs. Potato Head is to break this object up into very, very regular bits, send those bits through the internet, and then at the end of a myriad of journeys, you reassemble that artifact. And Patrick's prepared a wonderful animation that shows a more internetified version of breaking up Mrs. Potato Head. Okay. We then move on to layer 3. If you remember that layer 3, layer 2, layer 3 bundle, the TCP/IP protocols. The layer 3 is what we call the transmission, the transport layer, which is to do with transmission control protocols. This is all about managing the connectivity and the and error checking. So we've got the internet protocols, which are the sort of format of data. These govern the transmission control protocols, govern the actual the connections between a source and its destination, and is responsible for the error checking between it. So it's a bit like the telephony operator. If you notice here, unique sources and destinations on the internet are identified by what we call IP addresses. These are unique numbers that identify assets on the internet, and these are very critical in our work. IP addresses are basically a numerical label assigned to each device connected to a computer network that uses the internet protocol for communication. It gets quite circular here. This is where our domain names come into it, because IP addresses are not very friendly, but the domain name system enables names such as oxil.uk to be used as a pseudonym for an IP address. So it maps to a unique IP address, but it's something that people can type in and they can remember and link to without it just being sort of obfuscated numbers. We have a domain name query tool that's available on most computer systems called Dig, where you can type in Dig domain name and it will show you, here we've got the domain name oxil.uk and it's showing its published IP address on the internet. So when you see these websites, you can go and look up their actual underlying IP address, which is actually their unique address. Finally, the layer 4 application layer. This is about application protocols. For example, www is an application protocol that uses the internet, and this is an important difference. These are two people that developed different aspects of the internet. One is Sir Tim Berners-Lee, who invented the World Wide Web technology, and the other is Vint Cerf, who it very much developed with his team in America the sort of TCP/IP turnkey technology governing the internet. And they're both wearing T-shirts saying that they didn't invent each other's technology, because they often get mixed up and people often think that the internet is the World Wide Web and the World Wide Web is the internet. It isn't. The internet is analogous to a bookshelf in a bookstore, and a www is analogous to a populated bookstore that's full of rich information that uses and sits on the bookshelves. www uses the HTTP application layer protocol, the hypertext, I misspelt that, sorry, hypertext transfer protocol. There are others, POP3 and SMT for email, FTP for file transfer protocols, and you can see that at the application layer we start to get a rich mixture of different protocols. The protocols grow. So we have our internet, we have our 4 layers of the internet. The challenges that we're facing as an organization and as a world, I believe, are in new areas of security. There's still a plague of DDoS attacks. that are really that the internet underlying internet technology is not dealing with. We've got a lot of application layer attacks and viruses and phishing and all sorts of security problems that are starting to pretty much overwhelm the system and make the system uncomfortable to work with. There's the fragmentation of the internet. The key thing about these challenges is that this is where Oxford Information Labs is finding that we're getting more and more work and interest in what we do. People, when they come to Oxford Information Labs, are no longer looking for just techies. They are looking for governance people and people that can understand the challenges around the internet, but also have the backup of technical knowledge and technical experts, and so are working very closely with technical people. The dominance of the first movers. Some of the solutions that we're seeing are to use more and more of the big players who are already the winners in the internet, and less space for new people to come into the market. And things like we're very excited about AI and machine language and things like machine learning as technologies, but also the cost of encryption, the eco costs of encryption and machine learning and AI. And I also think internet governance is a big area. That's going to be another lightning talk from us. I think from Emily's side. There are a lot of challenges in internet governance. There are a lot of players who haven't been doing the job well or properly, and the problems are now coming to light. I think that's the heart of my lightning talk. Just to conclude, the internet is we've looked at the internet as a network of networks versus normal networks. We've found that there are key differences. There's no central control. The end-to-end principle applies. It's a permissionless and trust-based system. We've looked at the internet through the lens of 4 layers: the physical layer, the internet protocols, the transmission layer, and the application layer and their respective protocols. We've just had a quick flyby at how domain names are a pseudonym, can be thought of as a pseudonym for IP addresses, and we've reviewed the challenges of that. Before we have our chat, I just want to say thank you very much for listening to that. I know for those of you, and I'm talking to public and future people and clients of ours who take very deep dives into certain aspects of this has not been a fair or very expert look at some of those layers. But this is a flyby looking at the highlights that matter for Oxford Information Labs right now. And thank you very much for that.